Hi everyone, in this video I will show you how flash attention works using a simple numerical example. So the problem is that as context length grows, the attention matrix becomes huge and that can overwhelm the GPU memory. So flash attention avoids storing the full matrix by computing attention in blocks. So for example, it splits the input into multiple blocks and gradually builds the final output. So for this tutorial, I assume you know what attention is and how it works. My name is Abdul Salam and I'm a PyTorch ambassador. Alright, so flash attention uses the same attention formula, but it executes it in a different way. So this is the input that we are going to be using, and GPU runs fast. Flash attention divides the input into multiple blocks. So we are going to be having two blocks. Block 1 will have this GPU runs tokens. Block 2 is going to have this fast token, and it's also going to be our query for the attention. Normal attention takes in all of this input and performs the full computation, while flash attention will take in tokens from the first block and update some variables. We are going to see those, and then move on to the second block to update the variables. At the end, it just has to do a simple division to get the final output. Let's see normal attention on the left, and then we are going to see how it works on the right for the flash attention. Well, normal attention has this softmax. We take in this query times k transpose, then we multiply it by v, we get some scores. These scores are this query times k transpose, and we also can get the maximum of the scores. In the softmax, we can subtract from all of the scores, we can subtract the maximum, then we divide by the division of the summation of all the scores minus the maximum. This maximum, by the way, is just for numerical stability. So I have included this version that has this maximum just to show you how flash attention works when we also have this maximum. So this is the full version. At the end, for normal attention, all you have to do is multiply it by v. Now on the right hand side, let's see how flash attention does it. So at each block, we compute the query times k transpose. This k transpose are for just tokens in that particular block. We get the maximum, essentially this part of the normal attention. Then we compute an accumulator. This accumulator is essentially this part of the computation. So it's just going to be scores minus the maximum of all the scores, then we multiply by v. So in flash attention, we are actually multiplying by v earlier, and then we get a denominator, which is essentially the summation of all the scores minus the maximum. We do this at every block. At the end, all we have to do is to get the final output, divide the accumulator by this denominator. So this accumulator itself is like a matrix, a tensor, while this denominator is a scalar. So this denominator, for example, here is like this part of the normal attention. Okay, so since we are moving from block to block, we need some variables to keep track of our computation. For example, the maximum, this one, and the denominator, and also the accumulator. So we are going to be updating these variables at every block. In normal attention, this is the input, it takes in all of it. Let's say after multiplying by WQ, we get this minus 1 and 1. And let's say KV is this tensor. So for all of our input. In normal attention, everything is available for us. Now let's see flash attention. Well, the Q fast is going to be the same. After multiplying the representation of fast with WQ, we get minus 1 and 1, for example. We know that block 1 has two tokens, GPU and runs. Block 2 will have this fast token. For both block 1 and block 2 are going to be using the same query. We are in block 1. Then later on we'll move to block 2 till we get the final output. Let's continue. Normal attention computes the query times k transpose for all of the inputs that we have. Let's say after doing that, we get this minus 1, 0 and 1. So minus 1, for example, is the score for GPU. This is the score for runs, and this is the score for 1, for example. On the right hand side, flash attention, it also does the same, query times k transpose, but this k are from tokens in just block 1. So we are in still block 1. And after doing that, let's say we get minus 1 and 1. So we have essentially gotten this part of the computation. We have gotten the result, the score for GPU and runs. So later on, this part of the computation from normal attention, we will get it in block 2. Okay, so far so good. We will get it later on. As I have mentioned, we'll be subtracting from every score the maximum. This is essentially for numerical stability. The maximum is is 1. For normal attention, we subtract from the scores 1 and we get these values. And when we take the exponentials, we get this. The softmax will be those exponentials divided by the summation. Now on the right hand side, let's see how FlashAttention does it. We are still in block 1. We take the maximum. It turns out for the scores, the maximum is 0 here. The exponential, we need it because at every block we will be computing an accumulator and a denominator. So from every score we will be subtracting the maximum, and let's see, after doing that we get this value. So we are going to use these exponentials for our accumulator for block 1. But there is a problem. Notice that in here we are using a maximum of 0, but it turns out the real maximum is actually 1, which means that any computation that relies on this local maximum, we will have to rescale it later on when we figure out that the real maximum isn't actually 0, but it is 1. So in block 2 we figure out that the real max is 1, and we will have to rescale any computation that relies on this local maximum. So this is just that information I mentioned. Block 2 contains score 1, so the random max will actually rise from 0 to 1, and we'll have to apply this rescaling. We will see that. For normal attention, we know for the denominator we actually perform a summation. This is essentially the repetition of the softmax. When we do that, we get this. So this are the exponentials divided by the summation of the exponentials. We get these probabilities, then we multiply by the V tensor, and we essentially get the final output. So normal attention is done. Let's see FlashAttention. So we are still in block 1. Let's get the denominator, which is the summation of all the exponentials. After doing that, we get this value. Now let's build the accumulator for block 1. Well, normal attention is done. For FlashAttention, to get the accumulator, just multiply the exponentials by V, but this V are only for tokens in block 1. After doing that, we get this. So accumulator 1 relies on E, which was computed using a local maximum, which is not actually the global maximum. So in block 2 we figure out that problem, then we will rescale accumulator 2. So this is that information. Normal attention is done. Now we are in block 2 of FlashAttention. So we are actually going to be repeating the same query times K transpose. This K are for tokens in block 2, and we get this because the maximum is actually 1. So the maximum is like the old max, comparing the old max and the new score. Old max was 0, the maximum of them is actually 1. And then we compute the exponentials, which we will actually have to subtract the maximum, and we get this value. For the tokens in block 2, the V tensor is actually this, and then when we multiply the exponentials times the V tensor, we get this. Essentially, this is for computing accumulator 2. Okay, after multiplication we get this, and for building denominator 2 for block 2, the summation, we just have to take the summation to get this. So this will contribute to our running accumulator. This will contribute to our running denominator. So normal attention is done. For FlashAttention, we realize that the maximum is actually 1, so we need to get a scaling factor. To do that, take the exponential of the old max minus the new max, and then we get the scaling factor. So to rescale accumulator 1, just multiply it by the scaling factor. To rescale the denominator 1 that we got from block 1, just multiply it by the scaling factor. So now it is fixed. Both accumulator 1 and denominator 1 from block 1 are fixed. Block 2 will contribute this to our running accumulator, and it will contribute this to our running denominator. So accumulator 2 will be scaled accumulator 1, we have fixed it, and then contribution from block 2. Then we get this. Then the last denominator will be scaled denominator plus block 2's contribution. So this is essentially L2, somewhat like L2 from block 2. So now we are done with all of the blocks. Normal attention is done, while FlashAttention, to get the final output, just divide the latest accumulator and the denominator to get a similar result with normal attention. Alright, I will show you something on the PyTorch documentation. I am on the PyTorch documentation on scale.productAttention. So this is the function, but when I go down here, there's something interesting. It turns out that when you call the scale.productAttention, PyTorch actually selects a particular implementation based on your input. So for example, there is this memory efficient attention version. There is a C++ implementation version, and there is also FlashAttention-2. So what we saw is the core FlashAttention. This FlashAttention-2 essentially takes advantage of modern hardware to squeeze out more performance. Now when we go down here, it turns out you can actually force PyTorch to use a particular implementation. So for example, let's say you want to use this memory efficient version, you can call this function. All right, so there's also an important blog that I found on the PyTorch website introducing FlashAttention-3. So currently PyTorch supports FlashAttention-2. This blog is discussing a newer FlashAttention-3. They mentioned that FlashAttention has yet to take advantage of new capabilities in modern hardware, with FlashAttention-2, which PyTorch supports, achieving only 35% utilization of theoretical max flops on H100 GPU, for example. So they discussed some techniques regarding this Hopper GPUs, and they mentioned that we're excited to release FlashAttention-3 that incorporates these techniques that they mentioned, and there are more details underneath, and that this FlashAttention-3 is 1.5 to 2 times faster than FlashAttention-2 with FP16, for example. Now these are more details regarding the GPU, but when I go down here, there are some important charts comparing FlashAttention-3 with other implementations. So for example, here on the forward pass attention computation with head dimension 128 on H100 GPU, the purple bar is for FlashAttention-3. So in all of them, here on the y-axis we can see the speed. FlashAttention-3 is fastest. So they mentioned that we also look forward to FlashAttention-3 being integrated in future release of PyTorch. So you can also contribute to that on GitHub if you wish. Alright, thank you very much. I will see you in the next video. I'll put the link of this blog in the description. Bye bye.